In this video, I'll be going over questions 21 and 22 from paper 13, May-June 2018 for AICE Physics, syllabus code 9702. Question 21 says, the four graphs represent a progressive wave on a stretched string. Graphs A and B show how the displacement d varies with distance x along the string at one instant. Graphs C and D show how the displacement d varies with time t at a particular value of x. The labels on the graphs are intended to show the wavelength lambda, the period t, and the amplitude a of the wave, but only one graph is correctly labeled. Which graph is correctly labeled? So we can use this question as an opportunity to sort of, look at why the correct one is right and then kind of show why every other one is wrong here. So we see that x is being plotted on the x-axis here, and they tell us that that's the distance. So distance corresponds with wavelength, and so that's correct there. In other words, we get a wavelength from crest to crest if we're looking at distance being plotted there. We don't get a time period, and so the reason why A is incorrect is because we can't label this t for the time period if we're plotting distance x on the x-axis. So that's why A is incorrect. Now there's another reason why B is not the correct answer, but it's not because of this, it's because amplitude A is the distance from equilibrium up to, sort of the maximum displacement above or below the wave. It's not the entire sort of distance from the crest to the trough. And so that is what's incorrect here about B. If we look at C, we can see that they've labeled wavelength here, but they've plotted time. And so only choice D gets it right, where the amplitude is correctly labeled and the time period of the wave, capital T, would be the correct value if we're plotting time on the x-axis. So for that reason, D is the correct answer here. Question 22 says a cathode ray oscilloscope is used to determine the frequency of a sound wave. The diagram shows the waveform on the screen. The time-based setting is 5 milliseconds per division. What is the frequency of the sound wave? So if you've looked at the slides, you know that one of the learning outcomes is to be able to, determine the frequency by sort of looking at information on a cathode ray oscilloscope. So you want to look at an entire waveform. The time-based setting tells us how much time each one of these squares or divisions represents, and so 5 milliseconds per division. So we're really kind of seeing the time period of the wave. This is 5, 10, it's about 15 milliseconds, for one wave there. It's not quite perfect. We could probably do a calculation with the time period here is 15 milliseconds, and that would probably give us close enough to the correct answer that we'd be able to choose it out of here. But I'll show you sort of a more formal way to go about these calculations also. But just, so we can keep it simple, 5 milliseconds per division, we see one wave here, from where the wave begins to where it begins to repeat. That's about 1, 2, it's about 3 squares. So the time period, the time per wave would be about 15 milliseconds. And so the relationship between period and frequency is that they're inversely related, so the frequency is just 1 over the time period, and so the calculation is going to look like 1 over 15, and then milli is the same thing as 10 to the negative 3, and so a convenient way to sort of think about that calculation is 1 divided by 15. Now make sure that when you're using a value in scientific notation, you're plugging in your calculator using grouping symbols, because you don't want your calculator to divide by this and then multiply by 10 to the negative 3, but divide by that entire quantity. So 1 divided by 15 by 10 to the negative 3 gives us 66.6 repeating, and so that's about 67 hertz. And we can see that really none of those values is there. I mean, 71 is kind of close to it. Let's see if we can't do better over here. So if we look at this waveform, we can see that we get an exact sort of, match here. So this is half a wave if we go up to the amplitude, the maximum displacement, and then back down to equilibrium. So that's half a wave, and so we can see that there's 1 wave, 2 and a half waves exactly occupies 7 divisions here. So we can say there are 2.5 waves per 7 divisions. So if it's waves per division and we've got milliseconds per division, we can kind of cancel out the word divisions by saying it's like 1 division per 5 milliseconds. Now we have waves per millisecond. So the number of waves per time, that's the definition of frequency. And so frequency is waves per time. And divisions will cancel if we set up our calculation like this. So we multiply just everything on the numerator, divide by everything in the denominator. So we'll have 2.5 divided by 7 times 1 divided by 5, and then remember to convert milliseconds here. So computationally, we can look at this like 2.5 waves divided by 7 divisions is this, times 1 would just keep it as the same, divided by 5 milliseconds, and we get 71.4 hertz. And so a lot closer to sort of this answer. This gets us pretty close there. We can kind of, see that we're not quite getting the period quite right. It's a little bit less than that. So you don't want to just kind of eyeball it there, but if you made this value a little bit less than 15, you get a little bit closer here. But we can see that exactly matches it. It's just sort of more of an odd fraction. But by setting up the calculation more formally, we're going to get a more precise answer. So choice B.